Hello everyone, and welcome again to Pharmaceutical Calculations with Dr. Dave. In this video, we're going to be talking about instruments that are used for measurement. And for that, we have a few different things for liquids and usually for solids that we'll talk about. So when we are trying to measure something in pharmacy, we usually are going to select an instrument based on the level of precision that we are looking for. So we do use graduated cylinders or graduates in pharmacy. We might prepare something using beakers. We might dispense a product in a prescription bottle, but those have different levels of precision that we need to worry about. So when we are looking at beakers and when we're looking at prescription bottles, which look like this is a beaker, which you should know. These numbers on the side of the beaker are not accurate. They are estimates, and they're usually significantly off for what we would need for doing compounding in pharmacy and also for measurements in pharmacy. This here is a prescription bottle. This prescription bottle will have units of measurement on the side. This is the ml mark right here. This is the ounces mark here. And you will see our lovely symbol that you know for the amount that it is being used for. So our fluid ounce, and then you see the Roman numerals 3 after it. So it'd be 3 fluid ounces, which is where that top line right here would be. This is how we measure in one of these. It's not all the way up to the top, it's up to this first line that's right there. So these are not accurate, these are estimates. So the ones that we do use for much more accurate ones in pharmacy are those cylindrical graduates, and they will have markings with SI units. They're more accurate. There's also something called a conical measurement graduate, and I'll show you what those look like over here. So the ones over here on the right are the graduated cylinders. These are used for our accurate measurements in pharmacy. You could slightly less accurate are these conical vials. Conical vials will have different units, as not only SI on them, but the issue is that because this is cylindrical and it's very thin, the level of error of you reading it as well as the volume of the liquid in that error is a lot less the skinnier it is. So you can see a burette right here versus that conical vial, which has a larger overall circumference diameter, and you have a bigger error for reading, and therefore bigger volume error. So for us, we're looking at talking about those two for units of volume. When we're looking at units of weight, in pharmacy, what we do for weights is we're required to have a class 3, used to be called a class A, prescription balance. And this is typically what we're going to be using for compounding. These prescription balances used to be met with something called a 2-pan torsion balance, which you will see in the lab itself. A torsion balance will look like this. This is what a torsion balance looks like. You place weights on one side of the torsion balance, on this side, and you place your product that you want to measure on the left side. And when the two products are of equal weight, these two balance pans will be exactly centered like a seesaw, and that red line right there will be in the center of that display window. And when it's off, or one side is too heavy, that red line is going to be left or right. So these are called a torsion balance. It's the mechanism inside, which is where that name comes from. But what we want to be worrying about is two things that we're going to look at, and that is what is the minimum weighable quantity of an electronic balance, but also of these torsion balances. So the torsion balance will have that little display window that I showed you here. And as you place weights on the left side, that will move back and forth, telling you if you need to add more or need to add less. And when it gets to the center, you know that it's equal to the weight at which you have put on the right side. The terminology that we need for these types of torsion balance is something called an SR, or sensitivity requirement. And SR means the amount of weight that will cause that little red pointer to change one division, right? One division over. A division being one of these little slashes. So the amount of weight that it takes to move from one line to the next is called the sensitivity requirement. So how much mass you have to put on to move. It's like you jumping on a scale, where the scale, if it only measures in, let's say, grams, and you put 0.5 grams on it, nothing will display on the balance because it hasn't reached the minimum amount. So this red thing will move, but only when it gets to one of those lines is when we actually do a reading, not in between. So the SR requirement must be for these types of torsion balances 6 milligrams or less. So that means that when we place 6 milligrams on the balance, 6 milligrams must move, right, from this to here or more. It can't move less. So I can't put 6 milligrams on the balance and it be right in between two lines. It's got to be at least one division or anything over one division. So it must be 6 milligrams or more for an SR of a torsion balance. Now, for a single pan sensitivity requirement, so this is looking at a device that looks like an electronic balance. Single pan, meaning you have one single pan in the center here, and you're weighing something on an electronic device. For this, we don't usually use the word sensitivity requirement because there's no line for it to move against, but we do use the term linearity. Linearity is a value that tells us the capability of the balance to follow a linear relationship between the load and the displayed value. So what that means is that if I was to weigh 1 gram on this balance, right, and then I was to put a beaker on there, and then I was also weigh 1 gram with that beaker on there, so I am putting weight on it. And if I put a bigger beaker on it and I weighed that 1 gram, how is that 1 gram measurement changing over the span of this balance's capacity? So that's linearity is what we're looking at. Now, why do we need these two terms? We need these two terms because what's important in pharmacy is that we need to know what is the minimum weighable quantity that we can measure on these balances without our level of error being significant. And that point at which we say it's become significant is at 5%. So 5% is the maximum amount of error in weighing that we can have when we are making compounded preparations. So again, the minimum weighable quantity, we might abbreviate as MWQ, minimum weighable quantity. It is the smallest weight that will produce a predetermined weighing error. Now, we use 5% or less in pharmacy because that's what the USP document tells us that we should have for weighing for compounding. How we determine what the minimum weighable quantity is this equation right here for the torsion balance, and there's one for the electronic balance here. All it becomes is two numbers you need. You need, for the torsion balance, the sensitivity requirement, which we know for a pharmacy balance must be at least 6 milligrams. And the acceptable weighing error, we know in pharmacy compounding for weight, for weighing stuff, we can't have more than a 5% error in weighing. If you take 6 and you divide that by 5, so if I take 6 and I divide that by 5% rather, I am going to get 120, right? This is 120 milligrams. This percent, if I wanted to turn it into something, I can turn it into that 0.05. This is what would be the minimum weighable quantity of a balance if the sensitivity requirement is 6 and the measurement of error that we have is no more than 5%. I can give you a sensitivity requirement of 4. If your balance is the sensitivity requirement of 4, so it's a little more sensitive, your minimum weighable quantity will be a lot less. Or if you want to have a tighter percentage in terms of your error, so if I only want to have a 2% error in weighing, the amount you have to weigh is going to become larger. With an electronic balance, it's the same exact equation. The only thing you're substituting is, instead of SR, you're substituting linearity. Right? So The only thing that you have to worry about is whether or not it's a sensitivity requirement for a torsion, a linearity for electronic balance, and you put it over the acceptable weighing error. Make sure that when you do the weighing error that you do it in the decimal form. Don't keep it in the percent. In other words, don't do 6 divided by 5, right? It's 6 divided by 5%. So you have to convert this to the 5, or if it was another number. Okay, so let's do an example. It says calculate the minimum weighable quantity of a torsion balance with an SR6 and an error not more than 5%. We just did that up there. So why don't I just change this? Why don't I give us a 4? Let's say you have a torsion balance, it's 4. And for me, I want to have no more than a 2% error in weighing. What would be my minimum weighable quantity for a torsion balance? Well, I would take 4, because that's my SR, right? And I would put it over my percent error that I need. So 4 is my SR. My percent error that I want is 2, so I'm going to put that in decimal form. And I'm going to do my calculation is 4 divided by 0.02, and that'd be 200. So that means 200 milligrams, right? The SR was in milligrams, is my minimum weighable quantity if I did it for 4 and 2, right? 120 milligrams was it before. So notice that if I have more percent, or sorry, if I have a stricter percent in terms of my error, and I have a more sensitive balance where 4 milligrams does it, right? Because of that 2% error, instead of a 5%, I have to weigh at least 200 milligrams of material so that I know that my error in weighing is 2%. Another thing that we look at with measurement is the error in our calculation, the percent error. So nothing that we're going to do is actually going to be exactly perfect. So when you see a product that's commercially made and the weight of a tablet, the weight of that tablet is never going to be exactly the same from tablet to tablet. There is some variation in that, or capsule, or the amount that you dispense or make. There is some variability in that, but what is our percent error in doing that, right? And we need to usually sometimes know what that percent error is, because it must usually be within some specific range. So in order to do a calculation for percent error, you would take this equation right here, which is the difference between the two values, the value that you want it to be, or the theoretical value, minus the value that you got, so the experimental value, the value that you weighed, and you divide it by the theoretical value, the value that you want, or sorry, the value that it should be, and you times it by 100, and you take the absolute value, because the numerator could be positive or negative. If it's negative, that means that your value is either lower or higher depending upon what the theoretical value was. You can look at it also a little more condensed. You could say that the percent error is just the error that you know. What's the error? What is the difference, right? And then divided by the quantity that you are desired times 100. So just the way in which you want to look at it. So if you were to have if you were going to make lollipops that were medicated, and each lollipop was supposed to weigh, in theory, 2.54 grams, and you weighed a lollipop, and that lollipop that you made, that you took out of your mold, it weighed 3.24, let's say, grams. The question would be that this is the theoretical weight. This is the weight that you said a lollipop that's medicated should weigh, and this is the actual weight, right? This is the one that it actually was. What I can do is I can take the difference between those, right? So I can do 2.54 minus the 3.24, and I'm going to divide that number by the theoretical, which is the 2.54. I'm going to take that and multiply by 100, and that's my percent error. I've got a 27.56% error in my weighing. Usually we like to see those errors less than 10% on a final dosage form. So 5% error in weighing, but 10% in the final dosage form. So here is what we would be doing the difference in. So let's take an example. Let's say a prescription calls for 800 milligrams of a substance. So you have to weigh out 800 milligrams on a balance. After weighing the balance, somebody else decided to go ahead and check how much you actually weighed. And they had a little bit more of a precise balance. And that balance said that it was actually 750 milligrams that you weighed, not 800 milligrams that you weighed. So the question is, what is the percent error in weighing? The way in which we're looking at it here is that the amount that it should be in theory, or the theoretical weight, is 800 milligrams. The weight that you actually weighed out, right, was, when somebody measured it, was 750 milligrams. The weight that it should be is 800 milligrams. If I take that absolute value, times it by 100, not 1,000, by 100, that'll give me my percent error. So the top number is 800 minus 750, which is 50, right? The difference between the numerators is 50. Divide that by my 800, and I multiply that by 100, and I've got 6.25. So 6.25% error. This is my error in weighing. Like I said, about 10% error in weighing on the final dosage form would typically be fine, but not for weighing of powders. We want to be usually less than 5% error in weighing, so that would not be appropriate. Right? Would not have been good. So keep in mind with weight and volume measurements. For the weights, we're looking at measuring things on torsion balances or electronic balances. And the minimum weighable quantity. Minimum weighable quantities is the least amount that we should be weighing without a 5% error or more, unless we have differences in our percent error that's acceptable. But for a torsion balance, it's sensitivity requirement, so SR over the weight, acceptable error. And electronic balance is linearity over the percent error in weighing. And our volumetric measurements, like we said, which are appropriate to use. Okay? As always, pharmaceutical calculation is the most important class you have, because it's the only one that counts.